So the second half of 12.1 will be about summations, or in other words, I guess I should say slash series. And in this lesson, hopefully, we should be able to find partial sums of sequences and talk about the shorthand notation of writing it called sigma notation. Can we write it, can we read it, and can we evaluate them? So let's talk about the idea of a series. Now, yesterday we talked about a sequence, which was just a list of numbers. A series is it can be thought of as the sum of a sequence. So if we list them out, a sub 1, a sub 2, a sub 3, a sub 4, dot 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 dot, this is a sequence. If you were to happen to add them up, a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot 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 dot, we call that a series. So that's just sort of like the vocab difference between those two terminologies, sequences and series. A sequence is a list of numbers. A series is the sum of numbers. Now, I did say that this topic, sequences and series, is basically taught in all levels of math, Algebra 1, Algebra 2, Pre-Calculus, because in calculus, you're doing this a lot. You're taking a look at a sequence of numbers or a sum of numbers a lot. So that's why we sort of study them. There's this thing called a partial sum. So let's talk about the partial sum of a sequence, and let's give its definition. So for any sequence, so for the sequence, and we're just going to use arbitrary terms, a sub 1, a sub 2, a sub 3, a sub 4, dot 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 dot, a sub n, the partial sums are, so that's the math term there, partial sums. We use a capital letter S for sum. The first partial sum is adding up the first one number, which is basically the first term. The second partial sum is adding up the first two numbers. The third partial sum is adding up the first three numbers. I think you guys get the idea. The fourth partial sum is adding up the first four numbers, so on, dot dot dot, so on and so forth. The nth partial sum is adding up the first n numbers, dot dot dot, plus a sub n. And the way you say it is as you expect. S sub 1 is the first partial sum, S sub 2 is the second partial sum, S sub 3 is the third partial sum, so on and so forth, right? Now, the partial sums themselves may actually fall into a pattern in and of itself. So the sequence of the sums, right? So the sequence S sub 1, S sub 2, comma, S sub 3, comma, S sub 4, comma, dot dot dot, comma, S sub n is called, not surprisingly, the sequence of partial sums. Which means, since it is a sequence, we should be able to describe it using an equation, using a formula. So in this section, you're going to be asked to find partial sums and then look at the sequence of partial sums and see if we can't figure out a pattern for those. Let's take a look at this example here. It's going to ask you to find the first four partial sums. I wonder if I hit record. It would suck if I didn't. Okay. find the first four partial sums and the nth partial sum of the sequence given by a sub n equals 1 over 2 to the nth power. I guess I'll put my answer in a separate color. So before we find the partial sums, we sort of need to have the sequence laid out. Well, since they give you the explicit formula, I hope it doesn't take a lot of effort to realize that this sequence, actually no, I'm not going to use a different color. I'll put solution here. Okay. So I hope it doesn't take a lot to realize that the sequence looks something like 1/2, 1/4, 1/8, 1/16, 1/32 seconds, so on and so forth, right? All I did was plug in n equals 1, n equals 2, n equals 3, so on and so forth. So let's find the first four partial sums, and it should be fairly simple. You're just adding up the numbers. So s sub 1 is adding up the first one number. That's easy. S sub 2 is adding up the first four numbers. So if we do a little quick math, 1/2 plus 1/4, that's 2/4 plus 1/4 is 3/4. S sub 3, adding the first three numbers. So I'll go ahead and fast forward through this for you, but it's just literally adding fractions. So that's 6/8 plus 1/8 is 7/8. S sub 4 is adding up the first four numbers. So that's 14/16 plus 1/16 is 15/16, right? So here are the first four partial sums. Now it asks you to write the nth partial sum. So s sub n equals. Now the nth partial sum is to look at, excuse me, is to look at the partial sums as a sequence itself. So I need to think of 1/2, 3/4, 7/8, 15/16 as its own sequence. So this is sort of like the sidebar here. And ask yourself, can you come up with a pattern here? Well, we should know that's going to be a fraction, so I'll put a fraction there. The denominator are all powers of 2, so that's pretty easy, 2 to the nth power. And I hope everyone notices that the numerators are exactly one less than the denominators. So since we have an expression for the denominator, 2 to the nth power, to do one less, you do -1. So there you go. There is the formula for the nth partial sum. Now, again, I took this example from the textbook. They actually simplified it further. What they did was they split apart the fraction. So I guess I'll show the middle step. They split apart the fraction, and then they reduced that to 1. I mean, honestly, if you gave me this, I would be happy. I mean, I'd mark it as correct, but this is what they showed, which I suppose does look cleaner and nicer. There's only one place to substitute the n instead of 2. So partial sums are very easy. It's just like what you did yesterday, except you're adding them. First partial sum, only add one number, the first number. Second partial sum, add the first two numbers. Third partial sum, add the first three numbers, so on and so forth. The nth partial sum is just taking the partial sum as its own separate sequence and coming up with the rule, coming up with the formula. All right, so that's all it is. Let's just do one more example just to make sure you guys get the idea here. Find the first four partial sums and the nth partial sum. That just means find the formula of the sequence given by a sub n equaling 1 over n minus 1 over n plus 1. So to find the first four partial sums, we should probably find the sequence here. Well, let's see if we can't kill two birds with one stone. So let's go ahead and do that. So the first partial sum is just the first term. So what we're going to do is just plug in n equals 1 into here. So you get 1 over 1, which is just 1. I'm going to go ahead and just write it as 1, minus 1 over 2. And I know that equals 1/2, but sometimes when you leave it in the general formats, it might be easier to see. So we'll just go ahead and leave it like this. S sub 2. So the second partial sum is adding the first term with the second term. So we've already found the first term above. Now I'm going to add the second term, which again is just taking the formula and plugging a 2 into it. So if you do that, you get 1/2 minus 1/3. The third partial sum is adding the first three terms, but we've already found the first two, right, from the previous line. So we just go ahead and add the third term, which again, taking the formula and plugging in n equals 3. So that's 1/3 minus 1/4. And then the fourth partial sum, adding the first four terms. Which is taking this guy, plugging in a 4. Now the reason why sometimes it's easier to leave things in unsimplified form, especially if you recognize that, you know, there's a weird pattern to the numbers, is that you can sort of see the patterns a lot easier when everything's written out. For instance, let's take a look at the second partial sum, the second line. We have a minus 1/2 here and a plus 1/2. Well, they will cancel out. So what are we left with? 1 minus 1/3. Let's take a look at the third partial sum. The 1/2 cancels out, and then the 1/3 cancel out. So we're left with 1 minus 1/4. And then last but not least, in the fourth partial sums, the 1/2 cancels, the 1/3 cancels, the 1/4 cancels, leaving us with 1 minus 1 over 5. So for the nth partial sum, let's go ahead and write the sequence of partial sums. We have 1 minus 1/2, 1 minus 1/3, 1 minus 1/4, 1 minus 1/5. Therefore, the nth partial sum should equal, well, what do you notice about the sequence of numbers? Well, one thing that's constant is it's always 1 minus, so we can definitely do that. And it's always 1 minus a fraction, so we'll do a fraction bar here. And I think the other thing that everyone should notice is that the numerator is always a 1, right? So it's 1 minus 1 over something. So now all I have to do is come up with a description for the denominator. So for the first term, I want a denominator of 2. Actually, let me go ahead and write that in. So this is n equals 1, n equals 2, n equals 3, n equals 4. By understanding the term numbers associated with the fraction, I hope it's very easy and obvious to everyone that the denominator is always 1 more than the term number. So there we go. There's our formula. The denominator should be the term number, but 1 more. Right. So there's the nth partial sum. So here are the first, second, third, fourth. That's the answer I'll submit, and then the nth partial sum. Now, admittedly, all this writing gets tedious sometimes. What if I want to do the 7th partial sum, or the 12th partial sum, or the 50th partial sums? We don't want to sit there all day long writing out over and over and over again, right? So we have this idea. Given a sequence, say a sub 1, a sub 2, a sub 3, a sub 4, so on and so forth forever, we can write the first n, let's see, we're at the sum of the first n terms using something called summation notation, also called sigma notation. Those are the keywords there. Sigma notation is used as follows. Use the capital Greek letter sigma, looks like a fancy E. You have some sort of variable, dummy variable, doesn't matter, I, j, k. I typically use i's. You have to start at some number, in this case 1, and then you have to end at some number, and then you put your formula or your sequence there. This means take a 1, plug into the formula, plus take a 2, plug into formula, plus take a 3, plug into formula, plus all the way, rinse and repeat until you end up with the last number there. So that is the formal fancy schmancy definition of sigma notation. Let's actually break down what these letters mean. Right. So I'm going to go ahead and recopy the sigma notation. So obviously this part here will be your sequence formula or your rule. The I right here is a dummy variable. It could be I, it could be any letter you want, I, J, K, whatever. The important thing is it has to be the same letter that your sequence uses. So if my sequence uses, I don't know, X's, and then this little this on the bottom of the sigma here is a Y, then they won't play with each other. They won't recognize each other. They won't interact or speak to each other. The entire bottom portion is called the lower limit. It's also called the lower bound. It tells you start with plugging in I equals 1. So that tells you what to start plugging into. So if it was if there was an I equals 4 on the bottom, you would start plugging in at 4, and then you just keep incrementing up. On the top here, this is called, let me see if I can do it upside down. There we go. The upper limit, or the upper bound. This tells us to stop at I equals n. Right? Once you plug in I equals that number, then you can stop. And of course, the whole point of the sigma tells you to constantly add. Oh, tells you. Stop making it look like a G, Y-O-U. There we go. So that's sort of the breakdown of sigma notation. It looks very fancy, complicated math symbols, but I promise you, once you're able to read it, it's pretty straightforward. Again, it's just following instructions. So let's just do a quick example here, just so you understand how to read these things. Right, so just easy instructions. Find the sum. Nope, do I have the right color? Nope, I forgot to switch colors. There you go. Find the sum. So let's do letter A. Let's say I gave you a sigma. I equals 1 to 5 of k of I squared. Say part B, I gave you a sigma. J equals 3 to 5 of 1 over j. Letter C. Say I gave you a sigma. K equals 5 to 10 of k. Letter D, suppose I gave you a sigma I equals 1 to 5 of, say, the number 2. So it's just following instructions. So, oh man, sigma of I equals 1 to 5 of I squared tells you to start at the number 1 and just plug into the formula wherever you see an I. So it's 1 squared. That's it, I'm done. Sigma tells you to do a plus, and then you're going to increment from 1 to a 2 and do the same thing. Take I equals 2, plug into the formula, I'm done, do a plus, increment from 2 to a 3. So you keep increasing the number until you reach the top number. So that's basically it. 3 squared, 4 squared, 5 squared, and then since 5 was the upper bound or upper limit, you can stop, and then you just add them up. 1 plus 4 plus 9 plus 16 plus 25 is a 55. Letter B. The only reason why we're doing this example is to show you that we don't always have to start at 1. This sigma notation tells us, hey, start at 3. So plug in start at 3, and then just keep incrementing until you reach the top number. So 1/3 plus 1/4 plus 1/5. Common denominator is, what's that, 60? That's a 47/60th. Right? And you cannot reduce that. Part C, k equals 5 to 10 of k. Just to show you, again, it doesn't really matter what letter you use, as long as the letters in the equations matches the letter of your dummy variable. So start by plugging in a 5, and then move up to 6, 7, 8, 9, and then lastly 10. So you do all that addition. What is that going to give you? 45. And then letter D might look weird because there's no i's in the in the equation. So this says start I equals 1 and change all the i's into 1s. What do you get? Well, if there's nothing to plug in, what's left over? It's that 2. Plus, change the I into a 2 and plug into the equation. Well, there's no i's to plug in, so what are we left with? Another 2. Plus, change the I into a 3, plug into the equation. There is no I to plug in, so what's left over? It's a 2. So I think you guys hopefully get the idea that's just constant 2 for every single term. I equals 1, 2, 3, I equals 4, I equals 5, I equals 6. So 2 plus 2 plus 2 plus 2 plus 2 plus 2 is, not surprisingly, 6 2s is 12. And, I mean, we didn't have to write it out. We can actually read it. This literally says add up 6 2s, and we should know that that equals 12. And just like with yesterday, they're going to expect you to be able to evaluate sigmas, and if they give you a sum, they're going to expect you to write the sigmas. And there is no, just like with sequences, there is no magical formula. It's you just got to know how to do it. It's seeking patterns, it's understanding patterns, etc., etc. So write each sum using sigma notation. Suppose they gave you, we'll just do this one at a time, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus 6 cubed plus 7 cubed. How to do this? The first thing you want to do is ignore the pluses, basically, and see if you recognize any patterns. So 1 cubed, 2 cubed, 3 cubed, so on and so forth. Do you recognize any patterns? As if you were doing yesterday's lesson, come up with a sequence. So I hope it's very obvious to everyone that the pattern is simply the number cubed. So I know that the sigma to this is sigma, and I need a dummy variable. We typically don't want to use n's because n's are special. So you can use anything you want: i's, j's, k's, b's, t's, s's. It really doesn't matter. I like i's. And in this sequence here, what was the very first number we would have to plug in? Oh, hopefully it's obvious. It's 1. At the very last here, what is the last number we plugged in? Hopefully it's very obvious. It's 7. And then what is the pattern? Well, we came up with the pattern. Now remember, the pattern has to use the same dummy variable. So I would not put n cubed. That would be wrong. Because I used i's, I would have to change the pattern to I cubed. Yeah, so you just change it to whatever letter you picked. So there we go. This right here represents that sum. Let's take a look at this next one here. Radical 3 plus radical 4 plus radical 5 plus dot 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 plus radical 77. Now this one seems pretty obvious too, right? I think everyone agrees that the pattern is square root. So a very obvious thing to write is I equals, what number did we start with? 3. What number did we end with? 77. And what's the pattern? The square root of I. Now, the idea with this problem is there is no unique way of writing a sum in sigma notation. Technically speaking, we can write it in infinite amount of ways, because what if I didn't want to start at I equals 3? What if I want to start at I equals 1? Well, then that means that formula is going to have to change a bit, because whatever I put into here, when I plug in I equals 1, it needs to give me a 3 back out. Well, 1 plus what would give me a 3? Well, obviously that would be I plus 2. Similarly, this upper bound here needs to be a number such that when I plug it into this formula, it needs to give me a 77. So since I've already defined it as I plus 2, what plus 2 will give me 77? I actually have to stop at 75. But what if I didn't want to start at 1? What if I wanted to start at 0? Again, what number would I have to add to 0 to give me a 3? Well, that's easy. That's plus 3. And similarly, for the upper bound here, what number, since I've already settled with plus 3, would I have to add to get to 77? That's 74. So all three of these guys are equivalent. All three of these will give you the same sum. So there is no right way or wrong way to do things. You just have to make sure that your summation describes the same sum. And it just, again, it's just like those sequence problems yesterday. It's a giant puzzle. There's no way of solving. There's no way of figuring it out. You just got to use logic. You got to think about it. Practice makes perfect. Good luck.